Hello everyone, my name is Prachi of class BSc Chemistry Honors. This is audio recording for visually impaired student. Topic is dienes. Introduction. Unsaturated hydrocarbons containing two double bonds are called alkadienes or simply dienes. Their general formula is CnH2n-2 and hence they are isomeric with alkynes. However, their properties are quite different from those of alkynes. Nomenclature. The IUPAC name of dienes are derived from the corresponding longest chain by replacing the suffix "ane" by "diene." The relative position of the two double bonds are indicated by the Arabic numerals. The numbering being done in such a way that the carbon atom of the double bond get the lowest possible numbers. The position of the substituents is indicated by placing the number of the carbon atom bearing the substituent before the name of substituent. Their common names are however given in brackets. For example, 1,2-propadiene, 1,3-butadiene, 1,4-pentadiene, 2-methyl 1,3-butadiene. Classification of dienes. Depending upon the relative positions of the two double bonds, dienes are classified into three categories. First, isolated dienes. Dienes in which the two double bonds are separated by more than one single bond are called isolated dienes. For example, 1,4-pentadiene, 1,5-hexadiene. Second, conjugated dienes. Dienes in which the two double bonds are separated by one single bond or dienes which contain alternate single and double bonds are called conjugated dienes. For example, 1,3-butadiene, 1,3-pentadiene. Allenes or dienes containing the cumulated system of double bonds, that is, double bonds between successive carbon atoms, are called allenes or cumulines. For example, 1,2-propadiene, 1,2-butadiene, 2,3-pentadiene. Structure of allene. The structure of simplest cumulated diene is allene C3H4. The terminal carbon atom are sp2 hybridized since each one of these is joined by a double bond. In contrast, the central carbon atom is sp hybridized since it has two double bonds. Thus, the two pi bonds, like in acetylene, are perpendicular to each other, whereas HC and HD are in the plane of the paper while HA and HB lie in the plane perpendicular to the plane of paper. If both the H atoms on each carbon or all the four hydrogen atoms in the molecule are replaced by different substituent, then the resulting allene do not have either a plane or center of symmetry. Therefore, such allenes are chiral, that is, their mirror images are non-superimposable and hence show enantiomerism. Relative stability of dienes. Structure of 1,3-butadiene. Heats of hydrogenation can be used to determine the relative stabilities of dienes. We know that alkenes with similar structure have approx the same value of heat of hydrogenation. For monosubstituted alkane, it is approx 125.4 kJ per mole. For distributed disubstituted alkenes, it is about 117.1 kJ per mole, and for trisubstituted alkenes it is 112.9 kJ per mole. For a compound having more than one double bond, it is reasonable to expect a heat of hydrogenation which is the sum of heat of hydrogenation of the individual double bonds. Let us consider the heat of hydrogenation of 1,3-pentadiene and 1,4-pentadiene. Both these dienes give the same alkane, that is N-pentane, on hydrogenation, but their heat of hydrogenation are different. 1,3-pentadiene evolves about 28 kJ per mole of heat less than 1,4-pentadiene. This suggests that the conjugated diene 1,3-pentadiene contains less energy than the isolated diene 1,4-pentadiene. In other words, 1,3-pentadiene is more stable than 1,4-pentadiene by about 28 kJ per mole. Similarly, the observed heat of hydrogenation of 1,3-butadiene is about 12.5 kJ per mole, less than the calculated value. Similar studies with other dienes suggest that conjugated dienes are more stable than the isolated dienes. Explanation: the extra stability of conjugated dienes over isolated dienes can be explained in orbital structure and resonance theory. First, orbital structure. Consider 1,3-butadiene as a typical example of conjugate. Each carbon atom in 1,3-butadiene is sp2 hybridized and forms 3 sigma bonds. Each terminal carbon atom forms 2 sp2 S CH sigma bond and 1 sp2 sp2 CC sigma bond, but each of the middle carbon atom forms 2 sp2 sp2 CC sigma bonds and one sp2s CH bond. As a result, each carbon is now left with an unhybridized p orbital. The sideways overlapping of the two p orbital on C1 and C2 and those on C3 and C4 form two localized pi orbital. Now, if all the 4 carbon atoms and the 4 hydrogen atom lie in the same plane, then there can also be a In other words, the pi electrons of 1,3-butadiene are somewhat delocalized. This delocalization of pi electron imports extra stability to 1,3-butadiene and other conjugated dienes, since each pair of pi electrons is attracted by 4 rather than 2 carbon atoms. On the other hand, in isolated dienes, each pair of pi electron is attracted by only 2 carbon atoms. That is, there is no delocalization of pi electron. Resonance theory. 1,3-butadiene can be regarded as a resonance hybrid. Due to contribution of structure second and third, it is expected that C1 and C2 and C3 and C4 double bonds of butadiene should have some single bond character, and C2 and C3 single bond should have some double bond character. This has indeed been found to be so. The C1, C2 and C3, C4 double bonds of butadiene are slightly longer as compared to the typical carbon-carbon double bond length of 1334 picometer in ethylene. Similarly, C2-C3 single bond of butadiene is slightly shorter as compared to the typical carbon-carbon single bond length of 154 picometer in ethane. Methods of formation of dienes. Dienes are generally prepared by a suitable modification of the method used for making alkenes. Some of these methods are discussed below. First, pyrolysis of cycloalkanes. Retrodiels-Elder reaction. 1,3-butadiene is prepared by passing vapors of cyclohexene over heated nichrome alloy. Second, dehydration of butane 1,3-diol. Acid catalyzed dehydration of butane 1,3-diol gives 1,3-butadiene. Butane 1,3-diol needed for the purpose can be conveniently prepared by reduction of ethyl acetoacetate with sodium amalgam or catalytically. Third, catalytic dehydrogenation. In petrochemical industry, 1,3-butadiene is prepared by catalytic dehydrogenation of N-butane, 1-butane or 2-butane. Fourth, dehydrohalogenation of 1,3-dichlorobutenes. Isoprene can be prepared by dehydrohalogenation of 1,3-dichloro-3-methylbutane with Isoprene may also be synthesized from acetone and acetylene by following sequence of reaction. Chemical reaction of dienes. The chemical reaction of isolated dienes are exactly similar to those of simple alkenes, since the two double bonds react independently as if they were present in different molecules. However, the chemical properties of conjugated dienes are somewhat modified due to the mutual interaction of the two double bonds. Some of the important chemical reaction of conjugated dienes are discussed below with the particular reference to 1,3-butadiene. First, electrophile addition to conjugated dienes. First, addition of halogens. Conjugated dienes such as 1,3-butadiene, when treated with 1 mole of bromine, give a mixture of 1,2 and 1,4 addition product. Very often 1,4 addition product is the major one. Mechanism. Like the addition of bromine to simple alkenes, addition of bromine to 1,3-butadiene also occur by a two-step mechanism. Step 1. In the first step, the bromonium ion Br positive adds to the terminal carbon atom of 1,3-butadiene, forming the more stable secondary carbocation. Addition to second carbon simply does not occur since it gives the less stable primary carbocation. The intermediate carbocation is allylic in nature and hence can be regarded as a resonance hybrid of two equivalent structures. Step 2. Since in the resonance hybrid, the positive charge is almost equally distributed between carbon atom as indicated in first and second. The attack of bromide ion can occur on either of these. If the attack occur on C2, 1,2 addition product result, and if it occur in C4, 1,4 addition product is formed. Addition of halosine acid. Like halogens, halosine acids also react with 1,3-butadiene to give a mixture of 1,2 and 1,4 addition product. Mechanism. Mechanism of addition of HBr to 1,3-butadiene is similar to that of addition of Br2 as discussed above. 1,2 versus 1,4 addition to conjugated dienes, rate versus equilibrium. We have explained above that the addition of Br2 and HBr to 1,3-butadiene give a mixture of 1,2 and 1,4 addition product. Now the question arises as to why 1,4 addition product predominates over 1,2 addition product at ordinary temperature. To answer this question, let us consider the addition of HBr to 1,3-butadiene at different temperature. The following are some of the salient features of this reaction. First, at 193 Kelvin, the addition of HBr to 1,3-butadiene give a mixture of 80% of the 1,2 addition product and 20% of the 1,4 addition product, whereas at 313 Kelvin, a mixture of 20% of 1,2 and 80% of 1,4 addition product is obtained. The relative amount of 1,2 and 1,4 addition product obtained at 193 Kelvin remain unchanged no matter how long we allow the mixture to stand at the same temperature. When the product mixture obtained at 193 Kelvin is heated to 313 Kelvin in presence of more HBr, the relative amount of the 1,2 and 1,4 addition product slowly change from 80:20 to 20:80. Although each product, the fact that at higher temperature the 1,4 addition product predominates over 1,2 addition product suggests that 1,4 addition product is thermodynamically more stable than 1,2 addition product. The fact that each product is converted to the same mixture on heating suggests that this mixture is obtained as a result of equilibrium between the two products. Since 1,2 addition product is thermodynamically less stable than 1,4 addition product, therefore 1,2 addition product is converted into 1,4 addition product at a faster rate than the rate at which 1,4 addition product is converted back to 1,2 addition product. In other words, the relative amount of the product isolated at 313 Kelvin are governed by their relative stability. Thus, the addition of HBr to 1,3-butadiene at 313 Kelvin is thermodynamically controlled. With these points in mind, let us examine the addition of HBr to 1,3-butadiene in little more details by drawing potential energy diagram. As stated above, the first step in the addition of HBr to 1,3-butadiene is the addition of a proton to give the allylic carbocation, which then gives both 1,2 and 1,4 addition product. Since E act is less for 1,2 addition than for 1,4 addition, the 1,2 addition product is initially formed faster than the 1,4 addition product. Now in principle, each product can undergo ionization to give back the same allylic carbocation, but the E act for the ionization of 1,4 addition product to allylic carbocation is much higher than for 1,2 addition product. As a result, 1,4 addition product will ionize much more slowly than 1,2 addition product. Equilibrium is finally reached when the rates of the two opposing reactions are equal. Thus, 1,2 addition product is formed rapidly, but also ionized rapidly, but even more slowly. In other words, 1,4 addition product once formed tends to stay and hence constitutes the product of the reaction at temperature high enough for equilibrium to be reached. Second, free radical addition. Like Philic addition. Conjugated dienes also undergo free radical addition reaction to give a mixture of 1,2 and 1,4 addition product. Mechanism. The reaction is believed to occur by a free radical mechanism. Step 1. Benzoyl peroxide is converted into benzoyl radical, which is further converted into phenyl radical. Step 2. The CCl3 radical thus produced adds to 1,3-butadiene. The addition to one of the terminal carbon atom is preferred since it yields the resonance stabilized allyl radical. Step 3. The allyl radical formed in step 2 then abstracts a bromine atom from BrCCl3 to complete the addition. In doing so, it generates a new CCl3 radical which propagates the chain. If the addition occur at C2, 1,2 addition product result in, and if the addition occur at C4, 1,4 addition product is formed. Birch reduction. Although an isolated double bond is not usually reduced by N liquid NH3, but conjugated dienes are readily reduced to 1,4 dihydroderivatives in absence of added proton donors such as ethyl alcohol. Similarly, isoproenes on Birch reduction give 2-methyl-2-butene. Diel-Alder reaction, cycloaddition reaction. One of the most important reaction of conjugated diene is the Diel-Alder reaction. It involves the concerted addition of a diene to a dienophile to form a 6-membered cyclic alkene. Dienophiles are usually ethylenic or acetylenic compound containing electron withdrawing groups. In other words, dienophiles are alpha beta unsaturated acid esters, anhydrides, aldehydes, ketones, quinones, nitriles, quinones, and nitro compounds. These reactions are also commonly referred to as 4 plus 2 cycloaddition reaction since they involve the addition of a 4 pi electron system to a 2 pi electron system. Diel-Alder reactions normally do not require any catalyst and generally occur on heating. Mechanism. Diel-Alder reaction does not involve ionic or free radical intermediates and does not require any catalyst and is also insensitive to the polarity of the solvent. It is an example of pericyclic reaction since it proceeds in a concerted manner involving a cyclic transition state in which bond making and bond breaking occur simultaneously. Factors favoring cycloaddition reaction. The rate of Diel-Alder reaction are accelerated by the following factors. First, presence of electron withdrawing group in the dienophile. The presence of electron withdrawing group in the dienophile favors Diel-Alder reaction. For example, acrolein with one electron withdrawing carbonyl group reacts at higher temperature as compared to malic anhydride which contain two such group react at a much lower temperature. Similarly, para-benzoquinone reacts with 1,3-butadiene at 308 Kelvin. Second, presence of electron donating group in the diene. The presence of electron donating group in the diene favors the Diel-Alder reaction. For example, 1,3-butadiene reacts with acrolein at 373 Kelvin while 2,3-dimethyl 1,3-butadiene with 2 electron donating methyl group reacts at 303 Kelvin. Stereochemistry. The reaction is stereospecific and the stereochemistry of the dienophile is retained in the product. Another important stereochemical aspect of Diel-Alder reaction is called endoselectivity. That is, in most of the Diel-Alder reaction, it is always the thermodynamically less stable endo product which predominates over the more exo product. In the endo product, the substituent in the dienophile lies underneath the molecule, but in exo product it is projected away from the molecule. Regioselectivity. Diel-Alder reaction between unsymmetrical dienes and unsymmetrical dienophiles are regioselective. In general, Diel-Alder reaction are ortho-para directing, that is ortho or para but never meta products are obtained. For example, one substituted butadiene give ortho product but two substituted butadiene give para products. Fourth, reduction. Catalytic hydrogenation of conjugated dienes give a mixture of 1,2 and 1,4 addition product with the 1,4 addition product predominating. However, the chemical reduction of 1,3-butadiene with sodium or alcohol gives mainly the 1,4 addition product. Polymerization. Like substituted alkane, conjugated dienes also undergo free radical polymerization reaction to form homopolymers as well as copolymers. But there are two striking differences in the polymerization of dienes relative to alkanes. First, the polymerization of diene can occur both by 1,2 and 1,4 additions of the monomers, though the latter mode predominates. Second, the polymers derived from conjugated dienes still contain the double bond and hence show geometrical isomerism. Third, the polymer derived through 1,4 addition of one monomer unit to another may give both cis and trans addition, through the latter mode is preferred. Thus, the polymerization of butadiene in presence of peroxides produces a polymer in which 80% of the recurring units are produced by 1,4 addition and 20% by 1,2 addition. Similarly, substituted dienes also undergo free radical polymerization, mostly by 1,4 addition, giving mainly the all trans polymers. Like isoprene, chloroprene can also be polymerized under free radical condition to give neoprene. Neoprene is an important substitute for natural rubber and is superior to natural rubber in being more resistant to oil, gasoline, and other organic solvent. Mechanism. Free radical polymerization of conjugated dienes occur by the same mechanism as the free radical polymerization of alkenes. Natural and synthetic rubber. Natural rubber is a polymer of isoprene in which all the double bonds have cis stereochemistry. The addition occurred by head and tail union of isoprene units is as shown. But the synthetic rubber obtained by free radical polymerization of isoprene has also trans configuration. We have seen above that the free radical polymerization of dienes give mainly all trans polymers. But by using coordination polymerization, that is polymerization in presence of certain special catalysts such as triethyl aluminium titanium trichloride complex, we can control the stereochemistry of the polymers. Thus, catalysts were discovered by Carl Ziegler and Giulio Natta in 1953 and were commonly called as Ziegler-Natta catalyst. Because of their discovery, these two scientists shared the 1963 Nobel Prize in Chemistry. By using Ziegler-Natta catalyst, isoprene can be polymerized to give a polymer which is almost identical to the natural rubber in its property. Besides homopolymers, dienes are also formed copolymers. For example, buta-S. It is a copolymer of 1,3-butadiene and styrene. The origin of the name buna-S is Bu for 1,3-butadiene, Na for sodium, which is used as polymerizing agent, and S stand for styrene. It is commonly called SBR, styrene butadiene rubber. It is obtained by copolymerization of 1,3-butadiene and styrene in the ratio 3:1 in presence of sodium. It is used in the manufacture of tires, rubber soles, waterproof shoes, etc. Second, buna-N or nitrile rubber. It is a copolymer of butadiene 75% and acrylonitrile 25%. It is more useful than buna-S since it is resistant to organic solvent. Vulcanization of rubber. Both raw natural and synthetic rubber are soft and tacky and become even more so in hot water. Their tensile strength and resistance to abrasion is also low and elasticity is maintained only over a low range of temperature. All these properties can be improved markedly by process called vulcanization. It consists in heating rubber with 5 to 8% of sulfur. The chemistry of vulcanization is complex but involves formation of sulfur bridges or cross links between polymer chains through their reactive allylic position. These cross links make the rubber hard and stronger and remove the tackiness of the raw rubber since the individual chains can no longer slip over the other but are instead locked together in a giant single molecule.